Good morning, everyone. I'm Quentin Dalaiden from Dalaiden in Belgium. And today I'm going to talk about how we can reconstruct the past climate variability in the Antarctic based on climate models and paleoclimate records through data assimilation. And first, I would like to thank the organizer just to give me the opportunity to present my work, but also my collaborator, especially Hugo, which is my thesis supervisor. So maybe we can start with a short context. As you probably know, over the past few decades, from the mid-20th century, we observe large climate changes in West Antarctica. One of them is the strengthening of the low-pressure system located off the Amundsen Sea coast, called the Amundsen Sea Law. And partly due to this deepening of the low-pressure system, we also observe a general increase of snow accumulation over the West Antarctic ice sheet, but with strong regional changes. For instance, we observe a large increase over the peninsula and the eastern part of the West Atlantic ice sheet, but we observe a decrease close to the Ross ice shelf. And the instrumental-based temperature reconstruction also show strong changes. So it suggests that there is a large widespread warning with two very hot spots, which are the peninsula and the West Divide. And the last but not least, we also observe a strong increase in mass loss due to the basal melting, so to the ice shelf melting, because of the intrusion of warm matter masses beneath the ice shelf. And to really understand what is the driver of this mechanism, we can rely on instrumental observation, but it's generally too short to really understand the mechanism at the roots. So we need to provide long-term time series to place these Western changes of the satellite era in a longer time context. And so for that, we need to rely on indirect observation of environmental changes, which are the paleoclimate records. In polar region, this is mainly ice core records. And over the last few years, maybe 5 or 6 years, there is a strong effort made by the paleo community to gather all the available records to reconstruct the past climate over the last few centuries. We have, for instance, the Dalaiden from ice core, which has a very common proxy to reconstruct the temperature, but it's not the only one. We have also now a strong interest in snow accumulation. And more recently, this year, I think, Liz Thomas and her team collected all the sodium records from ice core, which is a proxy of the atmospheric circulation changes. And we were also interested to use other type of records, in particular records located in the mid-latitude of Southern Ocean, in particular trimming records, because we can also have some information on the large-scale circulation. And at the end, we end up with more than 100 annually resolved records that span at least 3 centuries. And another characteristic of this database is that we have a strong spatial coverage over West Antarctica, but there is still few information for East Antarctica. The other thing is that paleoclimate records only provide information at the local time scale, where the ice core are drilled, for instance, and only for specific variables, but the full spatial picture of the change is still missing, as well as the driver of these changes. And here comes data assimilation. So as weather forecast, data assimilation aims at combining the information from observation, typically for a case paleoclimate records, and the physics of climate models. So we first start with an initial best guess that is drawn from model simulation, typically Earth system model that are constrained by the external forcing, like the natural forcing of volcanoes, but also the anthropogenic forcing. And the main advantage of climate models is that it provides all the variables to understand the change. So it provides temperature, precipitation, but also the winds and the sea ice, all the variables that are useful to understand the change that we see in paleoclimate records. But climate models are useful tools to understand what it could have happened in the past. But because these simulations are not constrained to follow the observation, the climate model has its own natural variability. So it doesn't give any information on the driver of an exact of the timing of the change. And so for the other side, we have paleoclimate records that provide this information, the timing of the change. So we combine these two sources of information with data assimilation. So in practice, the climate models allow us to spread the information from paleoclimate records in space, because we rely on the covariance of the climate models, but also in other variables, because again, we can rely on the covariance between the assimilated variables and the one that we want to reconstruct. So for instance, if we assimilate a snow accumulation record, we are also able to update the winds because we rely on the covariance of the model. So it provides variables, the reconstruction of the variables that cannot be directly observed. And probably the main advantage of data assimilation is that by relying on the physics of the climate models, the final reconstruction is totally dynamically consistent, and so we can understand in a physical way all the change that we observe from paleoclimate records. So here I will present a study that we did 2 years ago. We first assimilate all the ice core record, Dalaiden and snow accumulation, plus the 3 rings, to reconstruct the climate over the Antarctic over the last 2 centuries. In our mission, we put a lot of attention to use also a climate model with isotope to directly compare the isotope from ice core with the model. And for other variables, like for the tree rings, because the climate model doesn't simulate directly the growth of the tree, we have to apply some proxy system models to convert the proxy into a climate variables or the opposite. So here I show the skill of our reconstruction over the instrumental era, because paleoclimate records don't extend after 2,000 years. We have a very short validation period, only 22 years. So here the correlation coefficient for the mean sea level pressure, the temperature, snow accumulation, and also the sea ice extents. As you can see, we have quite a good skill for the 4 variables. It's not very surprising that we are able to reconstruct the temperature and the snow accumulation because we assimilate the Dalaiden and the snow accumulation. But by assimilating these variables, we are also able to reconstruct other variables like the winds and the sea ice, which are particularly important for the mass changes of the West Antarctic ice sheet. Here I show a plot to illustrate the potential of data assimilation-based reconstruction that are the linear trends for 50 years periods of the last 2 centuries for the 500 hectopascal per 8, the temperature at 700 level, and finally the sea ice concentration. Over the first periods, what we observe is a weakening of the Amundsen sea low. So the first plot on the left. And this situation is an anticyclonic situation, so it brings warm air from the north towards the continent to the Ross ice shelf. And so it is associated with a sea ice decrease in that sector, but at the same time, because this situation is also associated with the circulation from the continent to the Bering Sea, we observe a sea ice extent increase in that sector. And for the last period, it's almost the opposite situation, where we observe a strengthening of the Amundsen sea low that brings a very warm air toward the peninsula, which explains the sea ice extent increase in that sector. And at the opposite, we observe a sea ice extent increase in the Ross Sea, just because the air is coming from the continent. And for the two other periods, we almost see no significant changes in the atmospheric circulation, but still we observe a sea ice extent decrease in the Amundsen Sea. So it could suggest that this sector, the sea ice in that sector, is probably more influenced by thermodynamic processes and maybe more linked to the rest of the globe, more connected to the rest of the globe, which is less the case for the Ross Sea. And because the Amundsen sea low is a key driver of the variability of the continent, but also is a key driver of the ice shelf melting, because it directly influences the supply of heat from the ocean towards the ice shelf, it's very important also to look at the variability of the Amundsen sea low over the last centuries. Our reconstruction showed that there is a strong multi-decadal variability. And starting from 1940, we observe a deepening of the Amundsen sea low. It's quite clear that we have a more cyclonic situation since the mid-20th century. And because this result was quite interesting for us, we wanted to know if this recent deepening of the Amundsen sea low can be attributed to the forcing, so to the anthropogenic forcing, for instance, or it was just part of the natural variability of the climate system. For this purpose, we conducted quite recently a detection and attribution study that aims at quantifying the role of the forcing in the observed changes and to compare with the natural variability of climate systems. We first compare our paleo-based reconstruction with two large ensemble of Earth system models. As you can see on the plots on the left, we have relatively a good agreement between the paleo-based reconstruction and the models for the trends. So it suggests that the trend is a forced response. And to look at more details, on the right, you can find the scaling factor for the different forcing. So how you have to interpret these results when the scaling factor doesn't cross the zero line, so the continuous line, it means that we can attribute the observed changes to this specific forcing. And for the specific forcing, for instance, for the greenhouse gas forcing, the scaling factor for this specific forcing is in black, while for the gray is all the forcing except this forcing. First of all, what we see is that the deepening of the Amundsen sea low is a forced response because the scaling factor for all forcing doesn't cross the zero line. And our results also show that the main forcing that are responsible of this deepening of the Amundsen sea low is the stratospheric ozone depletion. So it really links the paleo, so the past variability, with the future variability of the Amundsen sea low. And because the sea ice is also a key component for the variability of the mass balance of the Antarctic ice sheet, I just would like to show some results for the two key sectors in the West Antarctic sector. So first is the Bellingshausen and Amundsen Sea, close to the Peninsula Amundsen Sea. What we see is that we observe a sea ice extent decrease since the beginning of the industrial era. So it means that the western decrease that we observe over the satellite era is part of a long-term change. In contrast, for the Ross Sea, it was relatively stable, but it's only increased recently at the same timing as the deepening of the Amundsen Sea low, so around 1940. So it suggests again that maybe the Ross Sea is more related to the wind changes, while for the Bering and Amundsen Sea is more connected to the rest of the globe. Until now, I mainly talk about the long-term trends, but the variability, especially the multi-decadal variability, is very important, especially for the short, mid-term timescale. Over the past few years, 1 decade, I would say, numerous studies indicate a close relationship between the tropical variability, especially in the Pacific, and the West Antarctic climate. But most of these studies are based on instrumental observation, so it can only look at the year-to-year variability, but it limits us to study the multi-decadal variability. So in this study, we were interested in understanding the role of the tropical variability in the atmospheric circulation changes in the West Antarctic sector. And to do that, because until now we only use ice core record and also trimmings in the southern hemisphere, we also add now tropical records, in particular coral records, to have a constraint on the tropical variability. So again, thanks to a strong effort of PECHI's 2K working group, in particular here the Coral Hydro 2K, we have a lot of information from the tropics to have a constraint on the tropical variability. We have more than 80 records, especially in the Pacific, so it's very useful for us to understand the tropical variability on the West Antarctic climate. So here, what I show is an index of the interdecadal Pacific oscillation. This index measures the fluctuation of sea surface temperature in the Pacific, and on the bottom, the Amundsen Sea low. And here, I just also want to mention that because we are only interested in the multi-decadal variability, the force variability is removed. We only look at the natural multi-decadal variability. The first thing is that when we assimilate coral records, it improves a bit the rotation in the Antarctic, but not so much, which also means that the network of ice core in the Antarctic is already quite sufficient to reconstruct the Amundsen Sea low, or at least that the coral record doesn't provide a lot of information to constrain the Amundsen Sea low. As the other study highlighted, there is a strong relationship between the interval Pacific oscillation and the Amundsen Sea low at the internal time scale, but now we also showed that is the case at the multi-decadal time scale. And to further study the impact of the tropical variability on the atmospheric circulation changes in the West Antarctic, here I represent a composite of sea surface temperature and sea level pressure of a 30-year trend, only for periods where we observe a deepening of the Amundsen Sea low. First of all, what we see is that when we observe a deepening of the Amundsen Sea low over 30 years, is always associated with negative condition, negative phase of IPO, which represents a negative anomaly in the Central Pacific. And the mechanism that relies the two regions, it's simply the Rossby wave propagation that are triggered by this anomaly in the Pacific and start in the Indian Ocean with a low pressure, and then we end up with modification in the Amundsen Sea sector that impact the Amundsen Sea law. So according to our results, the multidegradability of the atmospheric circulation changes in that sector is fully associated with interdecadal Pacific variability. And we wanted also to know if the models are, what say the models about that. So we compare reconstruction with different climate models, 6 models, but here I only show the model of the American model, the CSM1 model. So we repeat the same diagnostic, and what we can see is that the model disagree with the reconstruction because the deepening of the Amundsen Sea law is not always associated with conditions in the central Pacific. So it can be related to our reconstruction that overestimate the link between the two regions, but by making sensitivity experiments, when we exclude coral records, so we have no constraint from the Pacific, we still observe this very strong association. So it can be either related to the model that are not able to reproduce this link between the two regions. And there is a consequence of this, is that we might largely underestimate the future atmospheric circulation changes associated with the IPO. So it could amplify or mitigate, depending on the phase of the Interregional Pacific Association, the force response of the atmospheric circulation. So now we know that the interdecadal Pacific Ocean is a key driver of the multidegradability of the Amundsen Sea law. What is the role in the full variability of the Amundsen Sea law? So not only the multidegradability, but the full variability over the last century. So here I represent again the two indexes that I showed previously, the Interregional Pacific Association and the internal Amundsen Sea law variability. So first what you can see is that when the IPO is in negative phase, we observe a deepening of the Amundsen Sea law. It's the wet patches. And the opposite when the IPO is in positive phase. And based on our previous study, we estimated the force response of the Amundsen Sea law. So we simply took the ensemble mean of a large ensemble and we corrected with U detection and attribution result. And so by combining this with the internal Amundsen Sea law, we can have the full variability of the Amundsen Sea law. And what we can see is that until the 1950, the Amundsen Sea law was only driven by the tropical variability in the Pacific, but after that, there is another component, a force component, related to the stratigraphic ozone depletion. So what we can say is that the deepening of the Amundsen Sea law over the last century has been first initialized by the natural variability, in particular by the Pacific variability, and then it has been maintained by the forcing. And finally, because until now, mainly only talk about the Pacific, I would like also to talk about other sectors, in particular the Atlantic. As I said at the beginning, now we have a new database of sodium record from ISCOR, and this database is very useful because we have more records, and we have also this record also cover a longer period. So it allows us to study the variability over a longer period. So we assimilate these new records, and here are the skill of our organization when we add these new records. What we can see is that we better we better reproduce the variability of the atmospheric circulation in the weather sea, but it's also the case for the sea ice concentration. We also have a very good skill in the raw sea. It's very important, these two regions are very important for the sea ice and the overturning situation. But still, we have some issue in East Antarctica. So here is our sea ice extent reconstruction for the weather sea in red. And we compare with the recent reconstruction of Warring Fog, which is only based on instrumental observation, the temperature, the pressure from the mid-latitude. And we were quite happy, both Ryan and us, I think, to see that there is a good agreement between the two reconstructions. Because for our reconstruction, there is no calibration against sea ice. It only comes from the proxy and the models that spread the information from proxy to the sea ice. About the variability, it's very closely related to the Amundsen sea law. We have very strong multi-declarability, especially starting from the 19th century, and a very big decrease of sea ice extent from the 1940. And when we look at the anomalies over 20 years, what we see is that the latest from our reconstruction sea ice extent anomaly is the lowest that we observe over the last 3 centuries. Now, I would like just to give some conclusion about this work and some perspective. So I hope I show you that the data assimilation is a powerful tool to reconstruct the past variability of the Antarctic, especially because we can provide a multivariate reconstruction. And also, I would like also to highlight that using different type of records is very beneficial for us because we have information for a wide range. And with these longer time scales, it allows us to investigate the role of the internal and the force variability, and so to have a better constraint on future projection, for instance, by evaluate climate models. However, I also would like to say that our reconstruction has some caveats. We mainly use continental records. So we may strongly overestimate the role of the atmospheric processes over the oceanic processes. So it really prevents analyzing the role of ocean dynamics. And one solution is to integrate marine records. So we have to discuss with paleoceanographers, but also to perform a fully coupled paleoanalysis to have the exchanges between the atmosphere and the ocean. And in a very near future, what we plan is because the ice shelf melting is strongly driven by the ocean. A lot of studies show that the changes in the ocean is also a response of atmospheric circulation changes. We want to use our paleo-based atmospheric reconstruction to force an ocean model to reconstruct the oceanic condition that could be further used to reconstruct the ice shelf melting. Thank you.
Thank you, Quentin, for this interesting talk. Are there any questions?
Thanks for a very nice talk. I'm just wondering, when you assimilate the data 18.0 from ice cores, do you consider the post-depositional effects like snow air exchange or diffusion?
You mean that like the wind distribution of the snow or
yeah, wind distribution or snow air exchange?
Yeah, so with data assimilation, we have the advantage also to provide some error to the data when we compare to the model. So the main error that we used, that we calculated in our data assimilation framework, comes from the representativeness error. So it means that the model is not able to reproduce all the small case processes that we find in ice core observation. So we take this into account when we assimilate ice core record, but also all the other records.
Thank you so much. Now this is on. Any further questions? I hope this talk was an inspiration to attend the panel discussion after lunch, because we're running out of time at this point. But yeah, hopefully this has sparked some thoughts and can be picked up after lunch. We're transitioning to the next talk, and that is by